Okay, hello everyone. We're going to evaluate this triple integral. And I think that one of the big things is we're going to find the triple integral over the solid region E. And we need to sort of pick apart and figure out what E is. And so we'll look at the planes that bound E and go from there. So first thing is we have x equals 4y squared plus 4z squared. So just on the side, if you remember z equals x squared plus y squared, this is a paraboloid that's facing up. Okay, I'm really doing a little cartoon of that. But that's if it's z equals x squared plus y squared. So we have, first of all, we're going to multiply this by 4, which just makes it more narrow. But the fact that I have I have x over here, not z, means that that this paraboloid opens to along the x-axis. So that, out of all my pictures, was a good one. Usually it doesn't come out quite so easily. And then we have x equals 4, which is a plane that's parallel to the yz plane. And all right, so I feel like I'm raising the stakes here in my drawings now. So oh, that didn't do anything. Let me see if I can, no. One more time, then I'm giving up. Okay, got that. So we have this plane here, z equals 4, and that might look, well, it's just a representation plane, but it's a plane that passes such that all the points on the plane have the x coordinate of 4. Alrighty, something like that. Okay, well, maybe, okay, the thing is that I have to stop spending too much time with this, okay. So anyway, that's z equals 4. So all right. This is x equals 4. And this right here is x equals 4y squared plus 4z squared. So for our region E, I'm getting that x is between 4y squared plus 4z squared. But that's incorrect. That's bounding it below, and x is bounded above by 4. Okay. Now, what we do on these is we we project this onto, all right, so see, this is x equals 4y squared plus 4z squared. This is x equals 4, and what we're going to do is we're going to project this onto the yz plane. So, well, that's a good question, is how can I explain that? Why do I know that? Why does it project there? Let me draw it. Okay. So see, it's going to project here onto D. And so, all right, x is a function of y and z in both cases for this top part and this bottom part. And so this is our that's sort of the top of our little thing right here, and then down here is the bottom. And those are both functions of y and z, and that's why we project onto the yz plane. And so what you can do also is you can see that the intersection, I'll move this down because I need more space. The intersection is something we can see sort of easily, that it's a circle or a disk. The boundary of the disk is a circle. So I have x equals 4y squared plus 4z squared, and I have x equals 4. And when I set these equal to each other, then it falls out pretty quickly that I have 1 equals y squared plus, it's these little tiny mistakes that are bad, not how to do those. So I have y squared plus z squared equals 1. And I almost don't think it's worth it to draw a picture. That's just a unit disk. Should probably keep the same colors that I drew the D up over in the other picture. So here's D. So this is the unit disk, R equals 1. All right, now, okay. So what I'm going to do when I write E is I could just write it like this: X, Y, Z, such that X and Y belong to the set D, which is shown there, and that X is between these two functions is shown greater or equal to 4y squared plus 4z squared less than or equal to 4. And now what I'm trying to do, I'm trying to evaluate this integral. So I have the integral of x dv over e. So this is the integral over d of the integral over x of x dx, all of that dA. Okay, and this is wrong right there. I was almost getting there, but okay, so we're going to integrate x dx, and the bottom bound is shown as 4y squared plus 4z squared, and the top bound is 4. So then I integrate, and I'm just going to sort of kick the can and not think about what d is, even though I know it's a disk over here. But I'm going to integrate x with respect to x, so that becomes x squared over 2. And then that is between 4y squared plus 4z squared and 4. And then I have dA. And let me just go ahead and put that in there. So let's see, we have a half I can pull out. And I put in 4 for x. And I put this 4y squared plus 4z squared in for x also. Okay, so that simplifies to, not too much too quickly. 16 minus, all right, let me point out I can factor out 4. Let me just not go too quickly. I have 4 squared, and then I can factor out from here the 4, but make sure I square it. And then I still have y squared plus z squared. Sort of didn't need to do that, but I sort of like almost like a compulsion to somehow simplify it. Quote, put that in quotation marks, simplify. Okay, now, and this is 4 squared divided by 2 is 8. Lots of things going on here, a lot of little things that can go wrong. But now, I feel like this is not really all that bad, because once again, if I draw this one more time for no real reason, it's just that I can't fit everything on the screen. If I had a big blackboard or whiteboard that I was working on, I could just point over a different part of the board. But anyway, here I have D, and D is, as we see, is a unit disk. I'm going to use polar coordinates. Of course I'm going to. Theta is between 0 and 2 pi, and R is between 0 and 1. I mean, it would be sort of madness not to use that, not to use polar coordinates. So this is 8 integral. So I integrate, theta goes from 0 to 2 pi, and then R goes from 0 to 1, and then I have 1 minus. Here's the thing where I did this before, and I got I got all mixed up. I'm not really having the very best day, but anyway, it's always a good excuse. But see, it's when we use our polar coordinates, we're using that y squared plus z squared is equal to r squared, because we have to rethink, and I didn't over here. I made a mistake here. I'm sorry. This is not x and y. This is y and z. Did I do the mistake up there? Okay, I didn't label it, but anyway, y and z. Okay, so it's x squared plus z squared equals r squared, because we're using y squared and z squared. And you might say, well, why am I doing that? Well, I know that d is sitting in the xz plane. So I need to rethink my polar coordinates with y and z. So since y is the horizontal axis, you have y equals r cosine theta, which I don't think we're going to use for this problem, and z equals r sine theta. Okay. And then over here, when I make the substitution, I have y squared plus z squared, and I replace that by r squared. Okay, then for dA, I'm going to write r dr d theta. But it's one of the reasons this problem is, a problem in the book, is that just by moving things around with x and y and z and using polar coordinates, it becomes confusing for me. And I think that's why it's a more difficult problem. Okay, so notice that there is no theta in this integral. I have in this expression here, there's no theta. So I can break this into 8 times the integral 0 to 2 pi d theta. And it's not just that there's no theta over here, it's also the boundaries have no theta. And then I go 0 to 1, 1 minus r to the 4th power, so r squared is r to the 4th, r dr. Now, if we integrate a constant, the integral of the constant is that constant times the difference of those endpoints. So this is 8, 2 pi minus 0 times the constant 1. And then over here, when I integrate with respect to r, I have to multiply that through, and I get r minus r to the 5th dr. And so this becomes 16 pi r squared over 2 minus r to the 6 over 6 from 0 to 1. Nice thing is when I put in 0 to r, then everything just disappears. Put in 1 squared, 1 to the 6, I just have 1. So I have 16 pi 1/2 minus 1/6. I'd be so happy if I get this right. Setting a low bar for myself, but anyway. 3/6 minus 1/6, 16 pi times 2/6, which is 16. I don't think it is right. Or maybe it is. Mr. Gloom and Doom. It is right. All righty. Okay. Okay. So let me point out that, was it that hard to draw this picture? A little practice. There's a bunch of these paraboloid figures. Z equals x squared plus y squared, but this is turned on its side. X equals 4y squared plus 4z squared. So we have that, and then we have x equals 4. We should easily be able to get that. Because these are functions of y and z, we project onto the yz plane in order to find our domain. And then you find out what this domain is by looking at the boundary that'll form the maximum, which will form the boundary of the domain. And you set these equal to each other. And so you get y squared plus z squared equals 1, which is a unit disk. So you set up the integral, and this gives the lower bound for x, the upper bound for x equals 4. Integrate. This actually shouldn't be such a big deal, but I often make mistakes. Then you get down to here, and you have over dA, and we now are using polar coordinates, but with our variables y and z when we make a conversion. So y squared plus z squared equals r squared. We never use these, but I think it's sort of good to point out that we would have y and z, not x and y, for our identities to go to polar coordinates. So then we have this simplified. Oh yeah, don't forget this r. That's super big, right? We need that r. That dA is equal to r dr d theta. Then you can multiply the r through. Okay, that wasn't so bad. Because we have this function we have a d theta, and this is theta. See, this part here has nothing with theta. So we can just do that, pop that out, do that separately, and then you integrate here. This is sort of a basic integral, fractions. Could be the hardest part, fractions. Okay, okay, I said something weird. I meant to say click, like, and subscribe. All right, well, I have these keyboard shortcuts. How's that one? That's a good one. And it's on the iPad. Can I think of more? I put these on my iPad, so you can do that too on your iPad or your iPhone. Make these little shortcuts on the keyboard. Go to your settings, general, look at keyboard, and it has something like keyboard shortcuts. Then you can just type something and then it comes up with this emoji. Or you have to paste the emoji in. Okay, anyway, that's all. Talk to you later. Bye.